Welcome to this explainer. If you're a high school student sitting in class, or honestly, just anyone curious about how the physical world actually works, you've probably looked at a whiteboard full of chemical formulas and thought, when on earth am I ever going to use this in real life? Well, today, we're going to answer exactly that. We are diving enthusiastically into the practical power of chemical math to see how it solves massive real world problems.
Let's start with a highly practical economic dilemma. Imagine you're a farmer, okay? You're running a massive agricultural operation, and to keep your crops growing and your business afloat, you have to buy fertilizer. Specifically, you need nitrogen. It's the absolute crucial active ingredient for your crops. But when you hit up the supplier, you're faced with a whole catalog of different chemical compounds, all with different price tags. So, how do you avoid getting ripped off? How do you actually know which chemical product gives you the absolute most bang for your buck?
This is where our hero concept steps in, percent composition by mass. Formally, it's defined as the relative abundance of a given element in a compound of known formula, but realistically, just think of it like a nutritional label on your food. You know how you check a label to see exactly how much sugar is hiding inside? It's exactly like that, but for chemical compounds. It's a foolproof tool that consumers, like our farmer, use to figure out the true amount of active ingredients they're actually buying. Consider these three really common choices our farmer might be looking at: ammonia, which is NH3, ammonium nitrate, NH4NO3, and urea, CH4N2O. Now, the global fertilizer industry is worth over $200 billion, so making the right choice here is serious business. All three of these fertilizers pack nitrogen, but they definitely don't contain the same amount of nitrogen per pound. To find our winner, the absolute most efficient choice, we've got to calculate the mass percentage of nitrogen in each one of these formulas.
Section 1, calculating percent composition, breaking down ammonia. Think of this as a simple recipe breakdown. Step 1, we find our parts. A single molecule of NH3 has one nitrogen atom. A quick glance at the periodic table tells us that one nitrogen weighs 14.01 atomic mass units, or AMU. Step 2, find the mass of the hydrogen. We've got 3 hydrogen atoms in this formula, each weighing 1.008 AMU. Multiply 3 by 1.008, and we get 3.024 AMU for the hydrogen part. Then we just add those two together to get our total formula mass, which is 17.03 AMU. Finally, step 3. We take the mass of our target element, the nitrogen, and divide it by that grand total. And here is the payoff. When we do that division, 14.01 divided by 17.03, and then multiply by 100 to get a percentage, we find that ammonia is an incredibly impressive 82.27% nitrogen. To put that into real-world perspective, if our farmer buys 100 pounds of ammonia, they're getting a little over 82 pounds of pure, crop-growing nitrogen. That's a pretty sweet deal.
We can easily perform this exact same math for the hydrogen in the compound. If we take the total mass of the hydrogen, that 3.024 AMU, and divide it by the total mass of 17.03, we get 17.76%. And here's a pro tip for your next chemistry test. Always check your work. Notice how 82.27 plus 17.76 perfectly maps out the entire molecule? It adds up right to 100%, the whole shebang.
Section 2, molecules to moles, scaling up.
Let's be honest, our farmer isn't buying a single microscopic molecule of ammonia, right? They're buying massive industrial tanks of the stuff. So the really crucial point here is that this exact same mathematical approach works whether you're looking at a single molecule, a dozen molecules, or an entire mole of molecules. We don't have to learn a new trick. We just swap out atomic mass for molar mass. Instead of measuring in tiny atomic mass units, we measure in grams per mole. As long as you have the chemical formula, you can scale this up as big as you want.
Section 3, the aspirin example, C9H8O4.
Just to prove how absolutely universal this chemical logic is, let's step off the farm and into your very own medicine cabinet. Let's look at aspirin. Given that the world consumes roughly 100 billion aspirin tablets a year, understanding what's inside is pretty significant. Following our recipe from earlier, we start by looking at 1 entire mole of aspirin, determined straight from its chemical formula. We calculate a total molar mass of 180.159 grams per mole. That right there is our denominator. It's the total pie. Just like before, we find our individual parts. We take the quantity of each element's moles in the formula and multiply by its molar mass. So for carbon, we've got 9 moles multiplied by 12.01 grams per mole. For hydrogen, it's 8 moles multiplied by 1.008 grams per mole. And for oxygen, 4 moles multiplied by 16.00 grams per mole.
Once we have those three separate totals, we simply divide each one by our grand total of 180.159. Check out how beautifully this pharmaceutical drug breaks down. Aspirin is exactly 60% carbon, it's 35.52% oxygen, and it's 4.476% hydrogen. And yep, when appropriately rounded, those percentages sum up to exactly 100%. We just decoded a complex painkiller using literally the exact same simple math we used to evaluate farm fertilizer.
Section 4. Test your knowledge. All right, now it is your turn to put on the chemist's hat. We're going to apply this structured logic to a brand new problem. Here is your challenge. To 3 significant digits, what is the mass percentage of iron in the compound Fe2O3? Take a quick second to think through the recipe we just practiced. First, you need to find the mass of the iron, and heads up, there are 2 of them in that formula. Then, find the total mass of the entire compound by adding up the iron and the 3 oxygens. Finally, just divide your iron total by your grand total.
Okay, if you followed that logic, mapping out your numerator and your denominator, you'd find the answer is exactly 69.9% iron by mass. What does that mean in the real world? It means if you're holding 100 grams of this compound in your hands, almost 70 grams of it is pure iron. Which brings us to our final big picture takeaway. The next time you see a chemical formula written on a classroom whiteboard, remember, these aren't just abstract letters and numbers designed to make high school tests annoying. No, they are the literal blueprints driving the world's economy. Whether you're a farmer trying to maximize your crop yield, a pharmacist analyzing aspirin, or an engineer sourcing pure iron, percent composition by mass is the exact mathematical key you need to unlock the physical world. And it makes you wonder, if a tiny little equation like this dictates the flow of billions of dollars globally, what other invisible mathematical codes are secretly running the world around you right now? Thanks so much for joining me for this explainer. I'll catch you in the next one.